Welcome to this lecture series in real analysis. In this lecture, we'll look at yet another criterion for continuity. And let us briefly look at what we have done. So first, we defined continuity via something called the geometric definition, or what I call the geometric definition. Then we showed that it is equivalent to the epsilon delta criterion and the criterion via neighborhoods. Okay, and let me not get into details of this. I'm assuming you have familiarized yourself with these pretty well. Here are two problems for practice. And now let us get started. So this is the main theorem that we want to prove. Just give me a second. Yeah, okay. So what is the theorem? Fix a function from a set S of real numbers to the real numbers and fix a point in S. Then the two statements written over here are equivalent. The first is that f is continuous at the point x0. And the second is, if xn is a sequence in the domain of the function, meaning each xn is an element of S, such that xn converges to the point x0, then the image sequence converges to the image point. Philosophically, what it is saying is that if xn comes closer and closer to x0, then the image comes closer and closer to the image of the point of convergence. So philosophically, it is capturing what continuity is all about. As you approach closer and closer to a point in the domain, you should approach closer and closer to the point in the image. Okay. So let's prove them in sufficient detail. Maybe I will not give too many details in this direction, but hopefully I will give all details in that direction. So first, let us look at why this is true. I'm sure you can write down all the details yourself. So what do we need to do? We fix a sequence xn converging to. So the sequence is in. So xn is a sequence such that, first of all, each point is in S, and second, it is convergent and converges to x0. And what do we want to do? We want to show that this is the case. Okay, and let's see why rather than write things. So xn converges to x0, and therefore whenever we have a delta neighborhood here, ultimately xn will reside in the delta neighborhood of x0. So we know that. But at the same time, so to prove this, what do we need to do? We fix some epsilon, and so to reduce this goal down further, we need to do the following: fix epsilon greater than 0. And now what we want to do, that this happens ultimately. So I've just used the definition of convergence. So this is what we will do. So fix some epsilon greater than 0. I have drawn the epsilon band around about the point x0, fx0. And we want to show this. Fine. Now by continuity of the function, meaning hypothesis 1, by continuity of the function, there is some delta neighborhood such that whenever a point is chosen in the delta neighborhood of x0 and in the domain of the function, the corresponding point of the graph is in this epsilon band. Okay, so there is some delta neighborhood such that the function kind of looks like that, as long as we are restricted to this delta neighborhood. Outside the delta neighborhood, the function may fly off, but within this delta neighborhood, the function respects this epsilon band, meaning all the points in this graph are in the epsilon band. Okay, now to finish the proof, since xn converges to x0, ultimately all the points of xn reside in this delta neighborhood. And therefore, ultimately all the points in the graph reside in this epsilon band. That is, these points, xn, fxn, they ultimately reside in this epsilon band, which is same as saying that fxn is ultimately at a distance less than epsilon from fx0, which is same as that statement. So this is basically the idea. As you come closer and closer to the point x naught, you must come closer and closer to the point fx naught. And this is a straightforward argument. But please write down all the formal details in your notes. Okay, now we will talk about the reverse direction. This is also just a matter of unraveling definitions. So let's take another page. So this time we want to prove continuity of the function at x naught, and we will go via contradiction. So suppose not, so that is f is not continuous at x naught. So then by the epsilon delta criterion, we can say that there is some positive epsilon for which no delta works. Meaning what? Meaning there is some special positive epsilon such that no matter what delta we pick, it doesn't happen that choosing, or rather I should say it the other way. So there is some epsilon positive such that no matter what delta we pick, there is always some offending point in the delta neighborhood of the point x naught. Right? Let me copy this picture from the previous page. So there is some epsilon for which no delta works, meaning what? If whatever you choose delta, there is always going to be some point in this delta neighborhood and in the domain of the function such that the value at that point, call this point x, such that the value at that point is far away from fx naught, meaning it is more than distance epsilon away from fx naught. So in the graph language, the corresponding point in the graph is outside this epsilon band. So whatever delta you pick, you can always find an offending point, a point which witnesses the failure of the epsilon delta criterion. So in particular, for each natural number n, there is some offending point in the neighborhood of width 1 by n, such that the image point is far away from fx naught. So I just wrote what I said. No delta works, so delta equals 1 by n also doesn't work. So there is some offending point in this region. Call that offending point xn. So for each n, we will pick up an offending point xn in this region and of course in the domain. So this is the meaning of offense. This is what offends the epsilon delta criterion. So we have that, but then xn is a sequence in S such that this is the case, and fxn does not converge to fx naught. So why is this the case? Well, xn is in the 1 by n neighborhood of x naught, and as n increases, this neighborhood shrinks. So xn converges to x naught. This you should be able to immediately see. Xn is a sequence in S simply because each xn is in S. So this is true. Xn is a sequence in S such that it converges to x naught. But this does not hold, what I want to say is that fxn does not converge to fx naught because this is the case for each n. For each n, fxn is away from fx naught. So fxn does not converge to fx naught. So we have justified this, and therefore this contradicts 2. This is a contradiction to 2. Because what 2 said was that if xn is a sequence in S converging to x naught, then fxn converges to fx naught, and this is in straight contradiction with it. So that's it. That's why 2 implies 1 is also true, and we have proven a new criterion for continuity. Okay, so all these 3-4 things about continuity that we said, all these various somewhat different looking statements, we will use nimbly. We may switch whenever we see one works better than the other or is easier to use. Okay, and let us just finish this lecture with some examples. Identity function. We can obviously prove the continuity of the identity function using the previous criterions, but in the the way we just proved, or the criterion we just proved, shows immediately that this is a continuous function, because if you pick a point x0 in the domain and you choose a sequence converging to it, the image sequence is the same as the original sequence and the image point is same as the original point. So tautologically we have this to be true also, and therefore the function is continuous at the point x0. So please make sure you follow the reasoning. The second is that fix any subset of the reals which is non-empty. Then this inclusion map which takes a point x to x. This is called the inclusion map. This is also continuous. And again, how do you show this? Fix a point x0 in the domain. Choose a sequence xn in the set S and converging to x0. So each xn is in S. We want to show that its image under the inclusion map, which is the same as this guy, converges to the image of x0 under the inclusion map, which is the same as this guy. So since xn converges to x0, we have xn converges to x0, and therefore the inclusion map is continuous at any point chosen in the domain, and hence it is a continuous function. Tautologically, the reasoning is almost tautological. And finally, the absolute value function. So why is it continuous? Fix a point in the domain and say, or let xn be a sequence which converges to x0. Well, then this converges to 0. Or you could also say that this difference is a null sequence as n increases. So that is the case, but that implies, but since this is less than that, this is a general fact about absolute values, we get that this also converges to 0. This is just the triangle inequality. Okay, so this also converges to 0. What's going on? This converges to 0 and this guy dominates that guy, and that guy is also at least 0. So this sandwich shows that this goes to 0. If you have been solving the exercises I have been giving you, you should be able to immediately see all of this. So that converges to 0, and hence basically what we have is that this converges to that, right? This being a null sequence means precisely that, and therefore we have shown the continuity of the absolute value function. We started with this and ended up showing that, and therefore the absolute value function is continuous. So just very simple applications of what we just discussed. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.